Hey there, coming back at you, team chemistry coach, with our continuation in our math in chemistry journey. Because you're going to do math all the time in chemistry. I mean, there's a good mix in general chemistry of quantitative type of work, which we're doing right now, versus qualitative. When we get to like molecular structures and parts of quantum mechanics, things like that. But a lot of chemistry is just applied mathematics using units and tracking uncertainty. Oh, what do we do? So last video, we looked at how to take any value or number given to you and determine whether it's exact or not exact. And if it's not exact, how many significant figures does it actually have? Because we need to know that when we're using it in calculations, right? Because when you're doing a calculation, you have to track the uncertainty. If you have a bunch of uncertain numbers going into a calculation, your answer cannot be certain. It's going to have some uncertainty. And you're always limited by the weakest link, right? So first thing I want you to do when you have whatever the mathematical calculation is, it's irrelevant. You're going to have to track uncertainty. But there's different rules for different mathematical operations. No, this is the biggest mistake in tracking uncertainty I find college students have, is they just immediately start hacking away. They go, oh, here's a problem, blah, 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 blah. And they just start whacking away in their calculator and don't even think about the type of mathematical operation they're doing and just throw mud at the wall and go, oh, just go by fewest significant digits. They didn't check and see if they were doing an addition or subtraction. Different set of rules, or a logarithm. Different set of rules. Oh, so you get your uncertainty wrong. First thing you always do, what is the mathematical operation that I'm doing? Understand that, and then think about the types of statistical rules in tracking uncertainty for that, because it's different for different math operations. So let's lump the two most common ones together on the same board here, and then we'll do an example of each one. And then normally I don't do logarithms at this point. I wait till we get to pH and whatnot. But since we're on a roll, let's do this. I ran out of room, but we'll do logarithms and exponents. 10 to the x, e to the x, those kinds of things for number 3. All right. Hopefully you've heard these terms already. Multiplication, division, probably the easiest one or a combination of both. And this is going to be probably the most common one we do when we do unit line equations through dimensional analysis. It's all multiplication and division. As long as you have multiplication or division or both, it doesn't matter. You're limited by the fewest number of significant figures or significant digits. So if you got 3 numbers going into it, count the number of significant digits in each of those numbers. The fewest one wins. That's what your answer is going to have, and then you round it appropriately. But if you're taking an addition or subtraction, and we're going to lump in averages in this, because when you take an average, say the average of 3 pennies, and you take penny 1, weigh it, penny number 2, weigh it, penny number 3, weigh it, technically cents, and you add those together and divide by the number of pennies. Well, when you're dividing by the number of pennies, if there's 3 of them, that 3 is an exact number. So in the division aspect of an average, there's no uncertainty. The uncertainty is all in the numerator where you're adding. So statisticians treat averages as addition problems as far as tracking uncertainty. Right? This is where most students have the biggest issues. Right? Either they apply the wrong rules by fewest sig figs, or they take, a lot of times in introductory chemistry courses, they'll just say, hey, when you're adding or subtracting, just go by the fewest number of decimal places. Yeah, that's okay, but it's not quite there. It's easier, I grant that. It's an easier way to think of it. It's just like, oh, that has 2 decimals, that has 3 decimals, that has 1. 1's the fewest number of decimal places, so I'm good to 1 decimal place. But not technically correct. It's okay if all of your values have decimal places, right? But what if one of your values does not have any decimal places? What if it's, 25,050? There's no decimal places in there. So how can you use that rule limited by the fewest number of decimal places? It doesn't work. Fortunately, in chemistry, in lab, most of the values we're dealing with have 1 or more decimal places. Yay! So you can pretty much think this way and be okay for the majority of chemistry. But if you ever run into that scenario where you've got numbers that you're adding or subtracting that don't have any decimal places, they're too big, you really should go by the largest absolute uncertainty. And most students want to vomit when I say that. All right? But if you really start thinking that way, fewest number of decimal places really is part of that. They're kind of one and the same thing, but going by largest absolute uncertainty works for every number you run into. So let's do a couple examples and apply these rules. Let's do our first example. Throw in some simple geometry here. Multiplication division example. Of course, I wouldn't tell you that on a quiz or test. You'd have to figure that out on your own. So let's say we got a gold brick and we want to measure the volume of it. Now, there's a couple ways we could do that, right? You could, if it's a brick, you can measure the length, the width, and the height with some kind of measuring device, a ruler, tape measure, whatever. Or if you know the mass and you know the density, that might be pretty quick. But we don't know the density here in this problem. We're given let's say we get a ruler, find out that its absolute certainty is good to 2 decimal places. So all of our measurements need to be to 2 decimal places. Review that video if you need to. So we say, hey, the length is 18.09 centimeters, the width is 11.42 centimeters, and the height is 5.40. So we could draw that if you want to. So here's probably not a real high brick, right? Pretty long. My Pictionary skills aren't that stellar. Imagine that's a perfect brick. All right, so we know that the length is 18.09 centimeters, right? Measure that out. We know the height. What's the height? 5.40. You don't have to draw this out, but it's always nice to have a picture of what you're doing. I never require you to draw this. And then we've got this width here. Boop. What's that? 11.42? Doesn't look like it's drawn to scale, but it goes back pretty far there. I would expect you would know the equation for this, right? So we know the volume is length times width times height. I do like you to write the equations because otherwise you're making the assumption whoever's reading your work knows that equation. They may not. You never know. Be crystal clear as a chemist, guys. That's our job. So length is 18.09 centimeters. Make sure you put those units in there, right? So a lot of students get lazy and don't stick the units in there and just slap them on the end. And I'm like, well, where's your units? Well, I could just do it in my head. I'm like, not everybody can do it in their head, right? Make it crystal clear. I need to see when I'm grading it and other people when they're reading it, they need to see why you get the units you get. They should make sense going through the calculations, right? Why do you get the uncertainty you get? Why do you get the number you get? 3 parts, right? The value, the uncertainty, and the units. Got to track all 3. So let's put our width in here, 11.42 centimeters. And let's put our height, which is 5.40 centimeters. Now, normally I would continue going to the right, but I'm out of board space. So I'll pop my equal sign down here. Let's take a look. Now, these are all centimeters. If one was in inches, I'd have to convert that to centimeters, obviously. So I got centimeters, centimeters, centimeters. So I'm going to end up with centimeters cubed as my units. I'm multiplying. Everybody agree? So I have, how many sig figs do I have here? Looks like 4 sig figs. You don't ever have to write that down. You can do that in your head. That's captive 0, so that counts. So 1, 2, 3, 4 sig figs. 1, 2, 3, 4 sig figs. Remember, non-zero digits always count. That's a trailing 0. Does that baby count? I see a decimal point. Yes, it does. 1, 2, 3. So that is 3 sig figs. And since we recognize the math operation as a multiplication, we go, oh, what's the rule for that? That's the one with the fewest significant digits. That's 4, that's 4, that's 3. 3 is the least. So I'm going to have to round my answer to 3 significant figures. Let's get our calculator. So let's take 18.09 times 11.42 equals times 5.40 equals 1,115.57412, blah, 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 it goes. But I only need 3 significant digits. So let's write the 3 ones. Put the vertical dash line there, and then a 5.5 centimeters cubed. Bam, goes the calculator. So that's greater than 5, right? So this is my uncertain place right there. So I need to round it to that third significant digit, which happens to be in the tens place. So is it closer to 1,110 or 1,120? Well, that's closer to 1,120. And I need that non-significant zero there without a decimal to maintain the magnitude. You can't round it to 112. That would make sense. You can't put a decimal point there because that would give it 4 significant figures. You need 3 sig figs. So that's why we have trailing zeros without decimal places to adjust the magnitude, right? But keep the uncertainty. If that is weird for you, just put it in scientific notation, right? So I could have just gone, let's see, 1, 2, 3 over. So you could have gone 1.12 times 10 to the third centimeters cubed. Right? And again, I do like you to box. Always give me the non-rounded or intermediate value, and I like you to box your final rounded value. It's so nice for your professors or TAs or whoever's grading your papers it draws their eyes to it. Boom! Right? Oh, so nice. And if it's wrong, I can go back, and if you've done everything, I can go, oh, you did everything right. Maybe you didn't count that properly for sig figs, and so I'll just -1 for sig figs or something. The clearer your work is, the more points I can give you on exams and quizzes, my friends. Right? Try to get in the habit. It doesn't take that long, right? You wouldn't have to write the rectangle there. You don't have to write the sig figs. You just give me the equation, pop in the numbers, boom. Doesn't take you that long. Let's do one with addition and subtraction. All right, let's do addition and subtraction problem. Let's say we get 3 statues and we win, right? One of them is 32.41 kilograms. There's a big one that weighs 134 kilograms and another that's smaller at 16.2 kilograms. What's the total mass? Total mass. So we got to recognize we're doing an addition here, right? We're going to add them together, which means we're limited by the largest absolute uncertainty, aka fewest decimal places, but that doesn't have any decimal places. So that simplified rule really doesn't pan out. We got to go by the largest absolute uncertainty. So you want to get real good. If you need to review that video on how to take any number and immediately tell its absolute uncertainty, you want to review that. So let's put this together. Let's take our 32.41 kilograms and let's add that to the 134 kilograms and the 16.2 kilograms. They're all the same units, right? If that was in pounds, we'd have to convert that to kilograms first, right? Let's take a look at the absolute uncertainty. Ready? Look for the last significant digit, and that is the uncertain digit. Where does that lie? Well, that 1 is the last uncertain digit, and that's in the hundredths place. So this is plus or minus 0.01 kilograms. So the uncertainty is in the hundredths place. Here, the 4 is my last significant digit. That's in the ones place. So this is plus or minus 1 kilogram. These are the absolute uncertainties. All right, just look for the last significant digit. In this one, the 2 is the last significant digit. That's in the tenths place, right? So this is plus or minus 0.1 kilograms. Right? You can't go by fewest decimals because that is 2 decimals, 1 decimal, no decimals. So that doesn't make any sense. But if we go by largest absolute uncertainty, 1 is bigger than 0.1 and 1 is bigger than 0.01. So this is my largest absolute uncertainty. So my answer is good to the ones place. Do you see how that works out? If that had been 130 with a 0, it would be good to the tens place. Ooh! So let's add these together and then we'll round it to the ones place. 32.41. Oh! The 2's not on there. Fartissimus Maximus. 32.41. There we go. I hate it when I hit a button and then it doesn't show up on my calculator. I guess I need to press harder. Plus 134 equals plus 16.2 equals. So 32.41. I think I screwed that up. Plus 134 plus 16.2. So do you get 182.61? I don't think you can see it with the glare on there. Right? 182.61. Yeah, so first time I did it, I typed it in, the number didn't show up. I'm like, but again, if that happens on a test, you get the number wrong. We're in the real world, the buildings fall down. But on an exam, if you set it up right and your number's off, I can see where you went wrong and give you a lot of partial credit for that. Because in the real world, you'll have plenty of times to do it over and over and over again. Probably use a computer or something. So 182.61. Let's write that down. Let me get my blue here. 182.61. But we're limited to the ones place, which is right here. So I'm going to draw a vertical dashed line right there at the ones place. So is it closer to 182 or closer to 183? Well, that's closer to 183. This is bigger than 5. So that rounds to 183 kilograms and box it up for me. Hey, nice. So that's how you do it. And you do the same thing for a subtraction. We should probably do an average because averages trip people out because your gut wants to do one thing, but your brain is telling you to do something else. So averages they'll drive you nuts. It just rubs you the wrong way. Still does for me. Another way you can do this is to line them up. Some people like to do that. I'll just scribble it on the board where you do like the 32.41 kilograms and the 134 and you line them up, right? And then the 16.2. Some people like to line them up like that and then just go like this. And then you just draw a line down. See that ones place? So you just go tick, 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 tick. And you just put the number right there. 182.61 kilograms. And then round it. You see how that lines up right there? I don't care if you do it this way. And you can do all this in your head. If you can do the uncertainties in your head, that's great. Or if you want to line them up and just draw the line down, I'm cool with that too. Up to you. Let's do an average. All right, let's pop this one out. You'll be doing averages quite a bit in labs, right? And when you do statistical analysis, if you do multiple measurements of an unknown and then you want to calculate precision for those kinds of things, or accuracy, you're going to do averages all the time when you do statistical analysis of your data if you do 2 or more measurements, which is pretty much every unknown we're going to do. So here's a typical example. What's the average volume of 3 containers, right, with volumes of one of them 525 milliliters, the other 14.7 milliliters, and the third one, 1,410 milliliters. No decimal point there. Right? Remember, when you're taking an average, you're limited by the largest absolute uncertainty, i.e. fewest number of decimal places, but I would always recommend going by largest absolute uncertainty. And I'm forcing you here because that is 1 decimal, that does not, and that certainly does not. So you're going to have to think in terms of largest absolute uncertainty in order to do this problem. Your gut's going to want to go by fewest sig figs because we do an addition on top and then you divide by the number of containers. So we're going to be dividing by 3. But the 3 is an exact number, so it doesn't include any uncertainty into the problem. So statisticians treat it like an addition problem. Right? So we're going to treat like an addition problem. Whoa, my shoulder went out there. I have trouble lifting on my shoulder. I need to actually have a shoulder. The doctor said I need an actual shoulder replacement. I need to have the bones sawed out and a new metal shoulder put in. I'm going to be a cyborg. So cool. Right? The other one's pretty bad too. But dislocated this one probably 3-4 times. Separated it a couple times. This one dislocated maybe twice. So I can barely lift this high. So every once in a while, if you see me writing and you see, like, did you see this one when I just dropped like that? Because I lifted it a little too high, and it feels like somebody's taking a knife and going, oh, and my shoulder drops. So just letting you know, don't laugh at the old guy. Right? I was like, oh, it happens sometimes because I coach baseball and I used to coach softball, and you know, I can't lift, I can't throw properly, so I got to throw a little sidearm. But every once in a while, you get excited, and I go to throw it like normal, and the ball just goes, because my shoulder hurts, and it goes like 3 feet away from me, and all the kids just laugh. Oh, coach can't throw. Like, everybody take a laugh. All right. So, but you gotta have fun, right? Can't wait. Gonna be a cyborg later. Woo! Okay, let's get back on track. You're like, focus locks. Focus. Yes, I had focus issues in school, but I still got my PhD. You can do it too if you have focus issues. It's all right. Let's see what we got here. Now, I'm going to show you the step-by-step, but I'm going to mention when I'm done to skip one of these steps because I'll show you where it causes people to have a fight between their brain and their gut. So let's take the average. What are our values? We got 525 milliliters plus 14.7 milliliters plus 1,410 milliliters. And we're going to divide that by the 3 different containers. So we're looking for the average volume of these 3 containers. Pretty different size containers, right? That's a little tiny one. So let's add these all together. Now, if we do that, we are limited here to the ones place. See that? Plus or minus 1. Limited to the tenths place, plus or minus 0.1, looking for the last significant digit. And this one, we're limited to the tens place. So ones place, tenths place, tens place. So we're limited to the tens place. So if we add those together, we get, probably be good if I typed it on my calculator. Let's take 525. There it is again. Erg. The 2 didn't show up. 525 plus 14.7 equals plus 1,410. You get 1,949.7. 1,949.7 milliliters divided by 3. And remember, this 3 is exact. There are 3 containers, right? Counting small numbers of objects. Now we're limited to the tens place. One's tens, so that's my uncertain place right there. Okay. This is where the gut goes wrong. We're going to do a division, so we want to go by fewest sig figs, but we don't. The statisticians say all the uncertainties in the top, so we're limited by the addition. We're limited to the tens place. So when we do this, we get 649.9 milliliters, limited to the tens place. So the dash line goes there. It does not go between the nines. It's not 3 significant figures, right? So and that rounds up to 650 milliliters. So limited to the tens place, you end up with 2 sig figs. Do you see how that rubs you the wrong way? It's like, I want to go 3 sig figs because I'm dividing. So my recommendation is to skip that step. I had to force myself to do that because I'm so trained to showing every single step. But because of the limitation of the rules on this one, if we show that step, we want to go division. So my recommendation is to do it this way. Get rid of that and just go straight to the answer. So just take 525 plus 14.7 plus 1410 divided by 3 and write the answer down. 649.9 milliliters. Going, it's an average, so I'm limited by fewest, the largest absolute uncertainty. Good to the tens place. Pop it to the tens place. And so that rounds to 650. So that will minimize some of the pain and anguish in your brain wanting to go one way or the other. Okay? So I'll save logarithms for when we go, because we're not going to do logs for a long time. Not until like I said, we do logarithms when we do pH. We do lots of logarithms in second semester general chemistry. So this, not necessary at this point. All right. So if you do happen to use a logarithm, check out the rules and whatnot, but we'll introduce that later. I think we're good for now.